Now we're going to talk about an application of molecule polarity. We're going to discuss what are called intermolecular forces or intermolecular attractive forces. Now this might be a review topic for you from Gen Chem, as often this is discussed in general chemistry classes. But like many of the other review topics that we're going to cover in the first part of this class, I'm going to need you to know it better than you did in Gen Chem. And we're going to use it a lot more. Okay, so what are intermolecular forces? Well, intermolecular forces are forces that operate between two separate particles. Now, those particles can be ions, or they could be molecules. And so that's why we use the term particles. Okay? Now, it turns out that atomic molecular sized particles are attracted together primarily by opposite electrical charges. Opposite charges attract. So all of these attractive forces are based on opposite charges attracting. This chart shows us the various types of intermolecular attractive forces, arranged from the strongest on top down to the very weakest on the bottom. What you're going to need to learn is, first of all, the names of the attractive force, what they consist of, okay, the order of strength, okay, and in some cases maybe be able to sort of describe some of the more unusual ones. In particular, this one, the hydrogen bonding, and this one, the London dispersion force. Okay, so let's start at the top. So if we're talking about a particle with a charge attracting a particle with an opposite charge, if those particles are completely charged themselves, they would be ions. So ions are particles that have one or more complete positive or complete negative charge. Since that makes those charges very large, and the strength of the attraction is dependent on the size of the charge, the ion-to-ion attraction is the strongest intermolecular attraction that there is. We could depict it like this, showing sort of a positive ion particle being attracted to a negative particle, where the dotted line is the attractive force. We would describe it as the attraction between two oppositely charged ions. And if we needed an example, we could say, for example, ionic salts like sodium plus, chloride minus, and the many other ionic substances that you discussed in Gen Chem. These are all examples of substances that have ion-to-ion intermolecular attractive force operating. The next attractive force then would be between an ionic particle, which has 100% of a charge, and a polar molecule, which overall is uncharged. The entire particle has no charge, but there are negative and positive partials on the ends. So what we would see, for example, is that if we had a positive ion, that would be attracted to the partial negative on the end of that polar molecule. So we would say this is the attraction between an ion and the opposite charged end of a dipole. In other words, the opposite charged end of a polar molecule. Now, a really good example of this is the attractive force that occurs when sodium chloride dissolves in water, where water is attracted to the sodium plus ion with its partial negative end, and it's attracted to the chloride minus ion with its partial positive end. And in fact, when we look at ions dissolving in water, which we're going to look at, for example, in lab, we see that you have this central positive or central negative ion, and then the water molecules use their polar ends and surround that ion to form a larger structure. I'm going to skip hydrogen bonding for just a moment. I'm going to come down here. If this is 100% of a charge and 100% of a charge. If ion-dipole is 100% of a charge to a partial positive or negative on a polar molecule, then the last one in this series would be a partial positive or a partial charge on the end of one molecule with the opposite partial charge on the end of the other molecule. And this is called the dipole to dipole attraction. So there's a trend, ion to ion because it's 100% of a charge, ion to dipole because it's 100% with a partial, and then dipole to dipole because it's partial to partial. We see this operating in polar liquids. I put water here. Water's not a great example because actually water is a really great example of this attractive force. But there are other liquids that are polar, but they don't do hydrogen bonding. And we can see that they have strong attractive forces in them. Okay, I now want to talk about the two kind of unusual attractive forces, or not say unusual, but ones that are based more on things within the molecules themselves. So we're going to start with hydrogen bonding. Hydrogen bonding is a very confusing term for people at the beginning because, first of all, it's not really a bond, and second of all, a lot of people get confused and think we're just talking about hydrogen covalently bonding to something, which is not what hydrogen bonding really is discussing. Instead, what we're getting in hydrogen bonding is we're getting polar covalent bond in one molecule being attracted specifically to a specific type of polar covalent bond in another molecule. So it's actually a polar bond to polar bond attractive force, where we get the partial positive end of one polar bond attaching or attracting to the partial negative end of another polar bond. Now, if I were to put it into words, we can make a very concise statement. It's the charge attraction between a hydrogen that is bonded to a strongly electronegative atom like nitrogen, oxygen, fluorine, attracted to an atom that has a lone pair. I'm going to flip over to the next page here, where I have some more details about the hydrogen bond itself. So first of all, I want to talk to you about a little bit of terminology. So hydrogen bonds actually occur between one particle or one molecule that we call the hydrogen bond donor and another molecule or particle that we call the hydrogen bond acceptor. Okay? A hydrogen bond donor is a molecule that has a hydrogen directly bonded to either nitrogen, oxygen, or fluorine. Now, because nitrogen, oxygen, and fluorine are extremely electronegative, that gives a very large partial positive charge to that hydrogen, right? So the nitrogen, the oxygen, and the fluorine, they get partial minus. The hydrogen gets a partial plus. We looked at that specifically in the case of the oxygen to hydrogen bond earlier. That hydrogen with the partial plus is going to be the donor part of the hydrogen bond. It's going to be the hydrogen end that's going to be attracted to a negative part in another bond. The hydrogen bond acceptor is going to be a molecule that has a second row atom that contains at least one lone pair and doesn't have a positive formal charge. So again, we see a lot of times that this is going to be an oxygen atom, either as part of that has just single bonds to it, or an oxygen atom that has a double bond to it, or a nitrogen atom with single bonds to it, or a nitrogen atom with a double bond to it, or even a nitrogen atom with a triple bond. One of the things we see, however, is that fluorine generally is not a good hydrogen bond acceptor. And that is because fluorine, its electron pairs are so strongly attracted to it, those electrons really don't exert their charge influence outside of the sphere of the fluorine. Now, to have a hydrogen bond, what we're going to need is one donor and one acceptor. Now, what we're going to see is that some molecules are capable of being both donors and acceptors. In particular, a really good example of this is a molecule that has an OH group, an OH bond within the molecule, can generally use the hydrogen of the OH bond to be the donor, but then it can use the lone pairs that are on the oxygen to be the acceptor. When molecules are both donors and acceptors, then the pure substance itself has hydrogen bonding in it, and we're going to see in lab that this has a dramatic effect on the physical properties of that pure substance. So I've drawn a picture here of how the hydrogen bonding might work between water, where we have one water molecule. It has a hydrogen with a partial plus. We have a second water molecule, a separate water molecule. It has lone pairs. The lone pairs, because they're clouds of electrons, have a partial minus. And that partial minus from that electron cloud is attracted to the partial plus on the hydrogen. Now, there are molecules that are only acceptors. So these are molecules that don't have OH or NH or FH, although there's only one of those bonds, okay? But they do have nitrogens or oxygens that have no hydrogens attached. So a good example would be a molecule like this. These are ethers, where we have the oxygen. They have two carbon groups directly attached, but no hydrogens directly attached. So ethers can use their lone pairs to be hydrogen bond acceptors. But because they don't have a hydrogen bond donor, inside the pure ether substance, there is no hydrogen bonding occurring. But if we take this dimethyl ether, this ether substance, and we mix it with water, which has OHs that can act as hydrogen bond donors, we would see a hydrogen bond forming between the OH bond in the water and the lone pair on the oxygen of the ether. And you can see here is that hydrogen bond, that attractive force. So this molecule can participate in hydrogen bonding. However, when the molecule is pure, there is no hydrogen bonding occurring. They only hydrogen bond when they're in a mixture with a different substance that can be a donor. Last, I want to talk to you about the London dispersion force. I first want to explain what it is, and then we'll talk about where it fits in the larger scheme of intermolecular attractive forces. So to understand the London dispersion force, it really helps to picture the electrons that are in a molecule, in its bonds and everything, as really being part of a cloud that's surrounding all of the little positive charged nuclei in the middle of the molecule. So we have this cloud. I sort of made it capsule shaped. It doesn't really matter. It's going to depend on what the overall shape of the molecule is. But we have this cloud. Now, this is supposed to represent somebody's eye. In other words, they're looking at this molecule. And when they look at this molecule, it turns out what they would do is they would look and they would say, okay, there's a positive charge there, but then covering up that positive charge is this cone of electron cloud that is between my eye and the positively charged nucleus. And in fact, it turns out that that cone of electron cloud will exactly balance out the cone of charge in the nucleus that is facing directly toward me. So we got this little cone of charge in here for the nucleus. We have a larger cloud of electrons. The positive here is balanced out by the negative there. So when I look at it, I don't see a charge. I just see sort of a neutral. However, molecules are constantly in motion. And when they collide with each other, what actually happens is the electron clouds come very close to each other. The electron clouds both have negative charges, so when they get too close, they repel each other. That's what causes them to sort of hit, is that repulsion gets too high and they bounce away. But the cloud itself is not hard, it's soft and squishy. So when they do that collision, they get dented. And typically what happens is we get a dent on one side and then somewhere else a bump pops out because the cloud has to go somewhere. Now, if we imagine looking at that same cone, we would see that now the cone of positive charge in the nucleus is the same size, but the cone of electrons is smaller. So now we have more positive charge, then we have negative charge, and so inside this dent we get a little tiny, way smaller than in a bond dipole, a tiny partial positive charge. Now, where the bump comes out then, we have the opposite effect, where on this side now, the positive charge stayed the same size, but now we have more electrons. So now, as we're looking in this direction, we see a little tiny amount of negative charge. Now, these are temporary. Eventually, that cloud will flow back into that space, that cloud will flow back into the larger cloud, and the little positive, partial positive, or partial negative charges will disappear. So these are temporary, okay? So we call these temporary, collision-induced, in other words, caused by collision, dipoles, right? Partial positive, partial negative. And they occur all over the surface of a molecule. So in fact, I don't know if any of you have ever seen sort of one of these pickles, right? Like you get at a deli or something, you pull the pickle out, and the pickle is sort of this shape, but it has all these bumps all over the surface. That's actually what the electron cloud kind of looks like. It's sort of this general shape, but then there's all these bumps and holes all over the surface. And those bumps and holes are going to cause us to have partial positives and partial negatives all over the surface of the molecule. Now, how does the London attraction occur? Well, it occurs because when the two molecules come close to each other, all of the little partial positives on one molecule become attracted to partial negatives on the surface of the other molecule. So, get a little attraction here, a little attraction there, a little attraction there. Each attraction is very weak, but because this occurs on the surface, there are many at the same time. And so the way I describe it is the surfaces become kind of sticky. They're not really glued together, but they're sticky. They kind of tend to stick together a little bit. That's the London dispersion force. Another way to visualize this is Velcro. If you've ever looked at Velcro, Velcro has two things. On one side, there's this sort of fuzzy, kind of, I don't know how to describe it. It's got like a fuzzy, soft side, right? And that's really just a whole bunch of loops of thread that have been kind of sewn together into little loops. Then on the other side, there's this hard plastic. Those are actually hard plastic loops that were molded, but then they have each of them has a little cut in the loop, so that when you push them together, the hard plastic loop gets grabs onto one of the loops of thread. And so they're kind of stuck together. Now, each individual hard plastic loop to thread interaction is very weak. You can pull it apart easily. But what happens with Velcro is there's a whole bunch of them. So when you stick them all together, if the surface area is big enough, it can become very hard to pull the Velcro apart. Okay, so now I want to slide up here back to our intermolecular forces diagram. So we can see that the net effect on hydrogen bonding is a little bit larger than the dipole-dipole force. When a substance can do hydrogen bonding, those particles tend to be a little bit more strongly attracted to each other than they are in the case of the dipole-to-dipole force. But when we look at London dispersion, it's a much weaker force. Even though we have lots of these little tiny attractions, they're just so small, they're nowhere near the amount of attraction even of a dipole, partial positive and partial negative. So here's the interesting thing. It turns out that almost all atomic molecular particles have electron clouds. In order to do London dispersion, all you need to have is an electron cloud. So literally every particle in the universe that has an electron cloud, and there are a few that don't, but most of them do London dispersion attractive force. It's just that when a pair of particles can do one of the stronger forces, the stronger force is so much stronger that the London dispersion force is essentially ignored. It's like a non-significant figure. In fact, if we look, these particles, compared to the London dispersion force is about 1,000,000 times weaker than these other forces here. So these are all on a similar order of magnitude, and then this one is much weaker. However, this is the default force. So what we say then is, or what we're interested in, is looking at a pair of interacting molecules and asking, what is the strongest force that would operate between these particles? And so, for example, if I have water where there's hydrogen bonding would be the strongest force. Does water do London dispersion? Most certainly it does, but it turns out the contribution from the London dispersion is so small that we can ignore it. It's hydrogen bonding that's important. But you'll notice that all of these forces require you to have polar bonds, polar molecules, or ionic charges. And we're going to see in organic chemistry that there are a lot of molecules that have none of these things. In that case, then, we won't have any of these forces operating, and the strongest force will be the London dispersion force. There are a couple other things I want to discuss about the London dispersion force. The first is that because London dispersion force occurs on the surface of particles, when you have molecules that have a larger surface area, they have a stronger total London dispersion force. So what that means is that molecules that are just larger, that just have more atoms in them, are going to have more and more London dispersion attraction. And so larger molecules, the larger the molecule is, they tend to stick together. The other thing to notice is that branching decreases the surface area of a molecule. Now, this is kind of a really terrible drawing trying to represent this, but if you imagine you took this molecule, you cut the end off, and you sort of put it right here, so that the rest of the molecule would be like right there, then you have an end right there, it would look like this, or this mushroom shape. What you would see is that before we cut it apart, we had all of that surface area right there. Now, when we look, because this is sort of rounded and this is sort of rounded, we have areas on the surface that are sort of, the surface is touching itself, but they're not available to sort of interact with another molecule. So the net effect is that making this branch, we hide part of the original surface and our surface area gets smaller. So branching decreases the surface area, therefore it decreases the strength of the molecule's London dispersion force. Okay, the last thing I want to talk to you about intermolecular attractive forces is that in general, what we see is that bonds and attractive forces decrease the potential energy of systems, which makes them favorable. Stronger attractive forces cause larger decreases in potential energy. Weaker ones cause smaller decreases. Okay? When we have several different particles attracted to a single particle in the middle, so for example, I used the idea of having a sodium positive ion and then a bunch of waters being attracted to that individual sodium positive ion. the total potential energy change is the sum of each separate water to sodium interaction. So what you can get is a situation where, although the force doesn't seem as strong, because there's more of them, the net effect of that force is larger than perhaps a more simplified force, but fewer attractive forces. And we're going to see that in lab when we look at solubility.